Hello and welcome back, and I have now installed a program called OBS, and that program records my screen. And also I have reduced the screen resolution to something that is not normal for this screen. So here we have Eagle, and this is a different design. Maybe I'll show you that first. So what I've done before, you have seen in my videos, you have PC case fan control X8. This is the board I made, and this is a board I made because not really because I wanted some new fan control on my PC. Well, I did want some, but it was more like making a board and getting back into electronics because it had been a while since. Challenge here was the USB interface. And also the microcontroller had to accept commands via USB. Set speed and store speed and power on speed and such. And also send back speed and power usage. So here you have the design. It has a frame, and here you have the microcontroller, and here you have the USB interface. So this is basically a USB to virtual COM port. So this is the board, and it took me a lot of time, but it was very educational. So you start by drawing the schematics, and then you go to the layout, and then when you have done that, you would then start routing stuff around on the board. I can show you. If I click this one, you can see the fill net. So all the magic happens in this microcontroller though. So let's look at the stripefix board. So the first thing we have to do is to make a schematic. So I have already started on it, and this is the connection to the other board. So this is basically an IC socket, and here you have the inverter. So this is one package. It looks like there's many, but it's IC number 3, and you know, one IC can have many parts though, so it's A, B, C and so on. And it also has power connections, so I could have connected all the bypass capacitors together on one net. It doesn't matter actually where you do it, but since in the layout later we want it exactly over this component, it's better to draw it like this, because then whoever reads this document in the future will know exactly what I'm intending to do. This is called a solder jumper. The solder jumper will then be an option. So we can configure this board later after the board is made and everything is fine. Let's say there is a modulator already, and then we don't connect the modulator part, and I don't have it in here anyway. Then we want this pin that goes down into the Commodore 64 to be connected to the device that will be placed on top of this. So therefore then we will do solder blobs here to connect these two together. So we jump it. So, and if not, if you want these pads to go out and be sort of handled out here, then we don't do this solder blob. So it makes it more flexible for us. So what I'm thinking is that I will clear this board and let's start over again. Now let's look at the IC socket. So there is a socket in here called IC package. Here I have made a special version of the DIL40 package. Let's look at the 40 package first. As we saw in this video here before, we saw that there was this ID fix or ID interface for the Amiga 500, and then in that interface they had the solution with a long or offset pins like this, and also they were like this. So the pin will go in here and to the bottom of the board, and then they soldered the IC here as an SMD type. So I want to do this. Let me just revert it. So what we do then is to copy this this board, and we have to click the copy button. Then this is equal, so this is a bit strange. Every program has its quirks, but this is how we do it. So we have to right click and then copy the group. So I have to select copy first. So here it is, but we don't want to paste it here yet. So therefore we can make a new package called DIL40 special Y, because I already made one there. So special Y, and then we hit the paste button, and then I will try and get this in the center now. So now I can then change it. We hit this change button here, and then select shape offset, change group. This, as I said, this is a bit strange in this program. You have to just work with it. So, but I like it. After a while, you will start to like it. So. There was a trick we did here, they did in the IDE board for the Amiga 500, and that was to make some of the pins not connected. So and also you did see that earlier, so let's do that. So that's pin 15 and 14. So that's pin 12, so 20, 19, 18, 17, 16, 15, 15. So let's change that to round. Then rounds. Now we can decide. So in our schematic layer we will put pads here, so that we will be able to connect the pins, and then with a solder blob or solder jumpers we can decide if these pads will come together. And as you can see here, this device has a package. If you have a datasheet, you will have a device, and that has different packages. So that's what's going on here. So what you can do is you can do new, and you can then, now we can find our the one we made, and then you have to give it a variant name. So let's call that YouTube variant. Okay. And now you will have to connect the pin that you have here with the pins that are here. So this looks a little bit, why do I have to just do this? All is connected. Now we have a device variant that we can use. So let's now hit OK on this one. IC package edit. There we go. So usually we don't make like a new package library, but I didn't want to tamper here, so but actually I should have done that when I think about it. So here we have our variant. So, and it's the same, so I will use the one I made earlier. Like this, boink, and you can add as many as you want, but for now we will keep the one. So now if we hit this button, we now can see that we have this part. Here, wire pads. and you have two different sizes. So, but this one was the one I thought about. So, yep. Let's go ahead and add two of those. And as I mentioned earlier, I didn't want to connect them directly, so therefore I want a jumper. And here you have you have one input, and then you can select which direction you want it to go by soldering here or here though. But I think this one's better. So let's try this one. So we then add two pads here, and now let's connect it up to the 14 and 15. So that's the Luma and the Chroma. So now we can decide if this pad here that is now connected to the VIC chip instead of the Commodore will go back to the Commodore or not. So let's go back and see what happened. So here you can see the pads, they are now on the board. So yeah, and these yellow wires, they're called rat's nests. And the reason for that is because we have these green wire nets that we are connected here. They will then be shown in the layout. So very helpful, because then you can do something like this and then know it will end up here somewhere. So yeah, and we will have to have that. We will have to have this pad very close to this pin to be able to solder the pin from the device above it. So, yep. This. So we'll figure out later what we're going to do. So just do thing here. So, and we don't want to make any routing now, but just to show you. This is how this works, and then the yellow lines disappears. So also it's not really. So let's this is called rip up, and this is to rip up what we routed. So we don't want to do that yet because we want to place everything first. So and now if I hit the middle button, then we place it on the other side of the board. So we'll figure out where it's best to put it. Okay, so finished up here. So and it looks very much the same. Okay, maybe this one is a bit high. Quickly value 10 microhenry. Okay. So you can see we have the IC here, the 74LS14, and if you remember the discussion from part 3, we talked about that when adjusting the signal, only use the very beginning of this resistor. So what we can do then, check it out. We can break this up, and we can take this one, and this one was here, it was 2K. So let's say let's say 2K here, or 1K8. What we can do now is to connect these together, and now this one, instead of having 2K here, we can have 200, right? So now we have 200 ohms to adjust here, and the rest that is not used is in this package instead, so we get a much finer control though. We don't need that multi-turn anymore because we used the multi-turn before because yeah, it was a waste. I'm looking at the design that they have over at the Lemon 64, and the one we have been looking at is from Forum 64DE, the German one, but at least the one from the German side, they have proper output stage for the Chroma, and here you have 1K in series, so well, this may work though, so but to keep it I think they solved it better here, so but I do like that they have a sort of a adjustment of the color here, so you can adjust the chroma if it's too much, but instead of putting it on the output here, what about putting it here? So I have actually tried that on breadboard and it works very nice, so let's go into the schematic and see what we can do. And we have chroma here, so let's bring that pot up here. If you now dial this up to the top, then this pot meter, then you will don't have any change at all. But if you now dial it down, then you will get a smaller chroma signal. The signal will then be lower, but because it has to pass this capacitor here, it will then be leveled with these two resistors, such that the only change you will see on this side is the amplitude, and amplitude is the saturation. So we are changing the saturation, and the impedance of the output stage will be the same as before, because this is a fixed resistor network. So if you had put like here, if you had put this in this arrangement, then we have changed the output resistance though, so that doesn't work as good. Yeah, so I think this I will go with it. I will go with this, and if this isn't good, then it's no problem, because you can just solder these two pins together, and they had 3 of those. They have T0. I have no idea what that is, but it would be nice to have a third of these. Even though it's not connected, we have the pads on the PCB such that we can do something about that later. We find that, oh my god, we need a third counteracting signal, and then we haven't have no pads for that, we just have to hack it. If we now add these components and we don't let's say we just make a pad here, then we can do whatever we want with that pad later, so we can make a bridge or something. Okay, so I've connected up this third inverter here, so and I have a pad for it, so we can experiment that whenever the board is finished. And yes, could have done this for all of this, but I think 3 will be enough. And also, when that pad is not used, you should ground it such that you don't get inputs that are. And talking about open inputs, we have now grounded all the inputs of the rest of the inverters now, and also connected power to that same package, IC2 as it says here. So yep, here's IC. Okay, so I have tidied up the schematics a little bit and put on a frame here, and usually I use A3 format paper frame, but this time I used the A4, so makes it a little bit more easier to read on the screen. So however, the schematic will be more cramped though. So, but I think this works great. So, and now I have placed the modulator part here and the stripefix part here, and now I will deal with soon I will deal with the connectors. So they will hook up to these modulator pins or labels. So and the point of this is the modulator is the core operation of the modulator is here, and then however it is connected, that will be done with these connectors, and we'll add labels that connect them, so you don't have wires all over the schematics here. But they will be connected even though there's no wire. So, and for example the AAC, that will have a label here though, so it don't run a wire all over the page. So sometimes that's much better than having wires. Other times it can be confusing, because when you start connecting things together, you don't really know what is connected beforehand. A third thing is the 5 volt, and as we know, the modulator pin connections, they are different. So in older revision you have 9 volt input, so then we need a regulator. And then if the board is used on a older revision of Commodore, then we need to bypass that regulator, so we need some solder jumpers. So we'll deal with that. But the main thing is that the rest of the circuit has 5 volts, so it's a matter of how we connect up the 5 volts down here with the input pins and the regulator. So yeah, and if you don't need a regulator, then we just don't solder it on the board, and it will be not connected. So I think you need a list of what needs to be done for what revision. Yeah. So it's time to connect up the power stuff on this chip, and I've been looking at the reference, the pinout, and I was looking for ground, and it's like one grounding point, and here you have analog and digital in the same chip, and you have one single grounding point. Also, that's interesting, because we think that it is the AC signal that is capacitive coupling into the Luma. But when you think of it, inside this IC, you have a lot of transistors that is used. This IC, you have like 12 address lines that is switched into output and inputs depending on the state of the AAC. So when that switches over, you have a lot of transistors in here that needs to change its state, and therefore you will have a large spike of current going down to the ground when that happens, also from the VCC, but more importantly the ground, because everything is referenced to the ground. So anyway, when you switch on and off the AAC signal, then the state of this address line will change from inputs to outputs, or tree state to outputs, and then you get a large current spike out here. And let's say now you have the modulator out here somewhere, and you take the Luma signal and into the modulator, and then you have a voltage supply for that, and you will supply ground to the monitor from this part of the circuit, and that is very far away from this circuit. So, and now imagine that this ground point is silent, or it's a very stable ground point, but here it's not. So therefore this Luma signal, which is a reference to ground, so if ground is bouncing up and down because of the AEC or the state of change on the address lines, then the Luma will also do that. So out here the Luma signal will bounce more in reference to the ground than it will in reference to this ground point. So that makes the question though, what if you took the ground from here instead of out here, and used that as a reference? Would that help? So that would be interesting to test though, but I don't know if I can do that right now, but I'll definitely try that later. Yeah. Right, so here we are. We have now tidied up here, and now we have all the outputs here. That will be, you can connect 3 wires and then run it over to the modulator if this board has been placed under the VIC chip. And then if we attach the board to the modulator pins as a modulator replacement, then we need to have these 2 ports here. So, and as you know, one of these pins are for 9 and 12 volt, or it can be 5 volts. So for the newer Commodores it's 5 volt, and for the older ones it's 9 or 12. So that's the thing though. Actually I think it's only 12, but anyway, 12 volt is the worst case though. So we need a 5 volt regulator here. So I've been at Mouser to do a parametric search for linear voltage regulators, and what we need is 5 volts. So let's go ahead and add a filter for that, and then what kind of current are we drawing here? So what I have calculated, and I have looked away from dynamic power dissipation. I'm only looking at static power dissipation. So for this part here, Chroma is pulling about 8 milliamps. Luma is pulling 36, mostly because of these 2 networks here and this one. And then you have this IC, and that's pulling about what is it, 21 milliamps, and in total that's about 65 milliamps pull on the 5 volt. So we need a regulator that can handle that. So what I've done here is to choose a 100 milliamp component. So let's apply those filters. Right, so now we have 230 match, and you have Maxime. They are this is for automotive products. They are quite expensive also, but what you can see, what's special with this one is you can have input voltage up to 72 volts. So that's pretty impressive. And but if you look at these cheaper ones, for example the small package, and then we look at the datasheets, and that's 42 euros. That's affordable. And then I was thinking about this package here, and this is the one we looked at here though. So now, how hot will this be? That's a very, very important question. So we calculated that it will be about 65 milliamps going through the liner regulator on the 5 volt. So if you take how many volts will there be over this regulator? So in the worst case we have 12 volt coming in minus the 5 volt coming out of the regulator. So that's, in worst case, you have 7 volts over the regulator. Now this is a very important question to ask, and that's how much power will this device dissipate, and that will also determine the limit. So we have to know if we are exceeding the maximum temperature this device can handle. So let's see, we have 7 volts over it, and multiplied by the 65 milliamps going through it, and then we have about half a watt. So this device will dissipate a half a watt. So let's say this is 0.46 watts. 0.46. Right, so let's have a look here now. Yeah, here you can see the package. It's a large ground pin here, way in and way out. And it's very easy to hook up. Maximum ratings. And I was looking at power dissipation, and it's internally limited. So what that means is it depends on how high the temperature inside the die will be, though, inside the package. What we can see here is our package here, SOT89, and you have thermal resistance, and then you have two values there. You have one for junction to case, so that means the die thermal resistance between the junction and the case inside the package. But what we want is thermal resistance from the junction, so that means the die, and ambient and the air around. So it's 55, and there's a footnote saying that you must consider 6 centimeters squared of copper board, and 1 cm squared, that's like the area of your index finger's nail. So if you have 6 of those, then you have so how can we get so much copper? Well, the thing is, this pad we're talking about, and let's look at that here. This is the recommended footprint of this device. That means the copper you need on your PCB. And here you can see this is the ground copper. So when you solder this, you will then get ground here and here. And if you think about it, this ground plane is the largest plane on the whole PCB. So I think we can manage 6 cm2 though. So, but now the question is, how hot will this junction temperature be? So let's have a look at that. Now, you see at 55 degrees per watt, we can calculate what the temperature rise will be. So we take 55 and then multiply by the half watt, and it's about 27.5 watt degrees Celsius. So, and now if the ambient temperature is 40 degrees, so we add that, then the junction temperature will be 67.5. So we are way beyond within limits. So even if you don't manage this 6 cm2, let's say there's 100 degrees Celsius per watt as the thermal resistance, and then you multiply that by a half a watt, is still within the so what is the upper limit then? Well, then you have to look here. the operation, the maximum rating, so that the max temperature will then be 125 before the thing pops. So yeah, so that's what we are, but the margining is so great here, so that's great. So let's select that device now. Alright, so after a bit of fiddling I did find the device. I did a mistake here because I searched for regulator, and then for some reason I got this positive regulator here and this one here, but since there's no note of there doesn't say regulator in the text, or it says regulators with an S. Then it doesn't show up. So that's I fool myself all the time. And so here you can see 78 and 78L. And now if I do this, then suddenly it appears, doesn't it? There. So yeah, that's a trap for young players and old players and old players, all alike. And here you can see that enlarged window. So the reason for this is this package will then be able to conduct heat more optimally. So yeah, so there you go. And now let's look at the board. Here it is. Looks nice. Now I had a large conductive plate to sink heat out of. So, and now I'll connect up the 5V regulator, and it has some stabilizing capacitors on input and output. And if the board shall not be, if it will be a newer Commodore, then we will have 5V, and then we can bypass with this solder jumper and not connect all these components. And also, if it's an older or newer, it depends on what's on pin 3 and 4 of the modulator inputs. For some reason Commodore has put ground on pin 3 on the the newer ones. And on the older one, there's on pin 3 there's Chroma input. So if there's an old one, then we put a solder blob here between 1 and 2, and you get Chroma out, a Chroma in. And then if it's a newer Commodore, then we have to put a solder blob here, because then the Chroma signal is on pin 4. So there we have a configurable option. So yeah, so here is the how it looks like in the layout. So it looks like the rat's nest is pointing up here though. So it's pointing at this component here. And now let's see what we have. And as you can see, this must be for another video, because okay, how will I fit all of this into this small area here? Well, at least there are 2 sides of this board so we can use, and yeah, so I think it will fit though. So, but we have to take care of the components that produce most heat has to be seated on the outside here. So, and also I will take care of having the analog stuff away from the digital signaling so it doesn't couple up any more noise. Yeah, so that concludes this video. So thank you very much for watching. Bye for next time.